a new situation that we'll find we want to work. We've gotten really good at dealing with degree 2 polynomials. Right? You can solve degree 2 polynomial equations just by looking at a degree 2 polynomial. You can sketch its graph. If you want to solve a degree 2 polynomial inequality, you know how to. Right, you can find the solutions. In fact, you can just look at one of the leading coefficients, positive or negative, and decide whether you want the space between or beyond. Presumably, though, one might occasionally want to study polynomials of degree bigger than 2. So equations like x cubed minus 5 equals infinity or something. That's what I want to do today. So let's just build the language. So I want to introduce the idea of high degree polynomials. Let's just start by building a pattern. A degree 0 polynomial is a constant function. So it's a function of the form, I don't know, q of x equal to c is often the letter for a constant. For example, I would call 5 a degree 0 polynomial. So degree 0 polynomials are just constants. What's a degree 1 polynomial? So it should be like a polynomial where the biggest power on xic is 1. That's about what degree should mean. So a degree 1 polynomial, we already have that. A degree 1 polynomial is something that looks like ax plus b. Another name for such a thing is a linear function. There are some examples. A degree 2 polynomial is a quadratic function. It's something that looks like ax squared plus bx plus c. Things that we're really quite familiar with. So there's a pattern that I'm building. What do you think a degree 3 polynomial should look like? Should look like that, but instead I'll start with an x cubed instead of an x squared. And it doesn't matter, like, I'm using the letters A, B, and C because they're the first letters of the alphabet, but it doesn't matter what letters you use for your constant. Ax cubed plus bx squared plus cx cubed plus dx. For example, then, I don't know, 3x cubed plus 4x minus 5x squared plus 6. There's an example of a degree 2 polynomial. Degree 3 polynomial, cubic function. And notice I haven't written the terms in cubed, squared, first power, constant form. But addition is commutative, so you could write that in that order. So that is still a degree 3 polynomial. A degree 4 polynomial, same thing, but I'll start at the fourth power. Ax to the fourth plus bx cubed plus cx squared plus dx plus e. And maybe, yeah.
Is it a degree 3 polynomial? Because you have degree 2, 3. Oh, no, on the left. No, on the left side.
Oh, there's no constant form, is there? So a degree 3 polynomial should be a bunch of constants multiplied by powers of x. Oh, I see what you're complaining about.
Yeah.
Okay, so that's technically not incorrect.
Okay.
It doesn't matter what order you write them, right? A thing times x squared plus a thing times x cubed is, you could rewrite that, you could flip the order of those two. But it certainly is a confusing order to write an abstract polynomial in.
So that is fine then?
Yeah, but I'm going to fix it anyhow. And I'm also going to put the constant term. Oh, I see. That's even worse. Okay. There were 2 cubic terms, weren't there?
Yeah.
Yeah, okay. ax cubed plus a square term, bx squared, plus a linear term, plus a constant term. Thank you for catching that. A degree 4, so the degree 4 polynomial is fine though, right? Okay.
Yeah.
So instead of embarrassing myself by writing another thing, let's not even write a general formula. Give me an example of a polynomial of degree 7.
So it would be 3x to the third plus 4x squared minus 5x plus 6.
This I put in the wrong order intentionally. Certainly, this would also be a degree 3 polynomial. 3x cubed plus 4x squared minus 5x plus 6 is another degree 3 polynomial. What I was trying to emphasize here is if someone hands you an example of a polynomial, the coefficients might be in the wrong order.
Okay.
Because you could rewrite this as 3x cubed minus 5x squared plus 4x plus 6.
Okay.
So the coefficients don't always have to be in the same in descending order because you can put them in descending order. So an example of a degree 7 polynomial, I don't know, 5x to the 7th, maybe I'll skip some terms, plus x to the 5th plus x to the 4th minus x plus 1. There's an example of a degree 7 polynomial. Everyone buy that? Is anyone upset that I skipped some powers of x? Right, because you could put them in. There's just a 0 next to them. Same reason as x squared plus 5 is still a degree 2 polynomial. In general, a degree d polynomial, so maybe I'll say it in words and then I'll write a formula, is any sum of constants times powers of x, where the largest power on x is d, there's the description in words, and maybe I'll write a formula with some ellipses in the notations. So in general, a degree d polynomial is something of the form a constant, maybe I'll call it the dth constant times x to the d, plus a d minus 1th constant times x to the power d minus 1, plus, I don't know how big d is, so I can't keep on reducing by 1 and hope to end, plus a1x plus a0. So if you don't like that, all that means is it's a sum. I've added a bunch of things together. Each of the things is a constant times the power of x. The biggest power on x is d. Cool. I think that's about as abstract as I'm going to get today. And let's just check some definitions. So tell me, are these polynomials? Is 5 a polynomial? This is show of hands. Yes? No. Yeah, it's a polynomial. What degree is that polynomial? It's a degree 0 polynomial. Constants are polynomials. You would just sooner study them as constants instead. Uh, 1 over x, is that a polynomial? Folks for yes? Folks for no? So it is not a polynomial. You might say, well, it should be, because it looks like it's x to the negative 1. That's like a power of x, right? But in all of the polynomials I've written, do any of the polynomials have negative numbers in their exponent? So polynomials explicitly forbid that. Not a polynomial. It certainly is still an important function, and a function which we can study. You can't study it as a polynomial. It'll have different behaviors than polynomials. 4x to the 5th minus x to the 4th plus 3x plus 2. Is that a polynomial? What degree is that polynomial? Yeah, it's explicitly a sum of a bunch of constants times powers of x. The biggest power on x I see is 5. X plus 1 divided by x minus 1. Is that a polynomial? Folks for yes? Anyone for no, I don't think so? It's not a polynomial. A polynomial can have like a constant in the denominator, but that's all you're allowed to divide by.
Even if you can make it into a polynomial.
Ah, so you're saying, well, what if I saw instead something like that?
Yeah.
So this is really close to being a polynomial.
Mhm.
The only reason, a difference it has between polynomials is what is the domain of this function?
What's it
Yes, everything except for -1. When you plug in -1, you get 0 divided by 0. So that's almost a polynomial, but it's got a hole in its domain. Certainly, you could study this by simplifying it to a polynomial, but then you would have to remember that I can't actually plug in -1. That makes sense? What about those 3 linear functions multiplied together? Does that give a polynomial? Folks, but yes? Anyone for no? Yeah, it is. And we could see exactly what polynomial it is, I guess, by foiling it out. I don't think I want to, because that'll just take too much time and space. But imagine if you did FOIL it out. What would be the biggest power you would see on x? So what's the degree of that polynomial? And the last one, 2 raised to the power of x. Does that look like a polynomial? Is it a sum of a bunch of constants times powers of x? No, it's a power of 2, but the power you take is varying as x varies. So in a polynomial, I see here a variable in the exponent. Polynomials only have whole numbers in their exponents. That seem okay? So that's what polynomials are. That's what we're going to begin studying at this point. We'll find that there's significantly less that we can do algebraically than we could with degree 2 polynomials. And when we try to do things just by algebra, things get complicated pretty fast. We'll learn that tomorrow and Friday. But you still see them, and you just have no choice but to deal with them somehow. For instance, let's just see one coming up. So let's suppose you start with a 3x2 sheet of cardboard. You make a square cut at each corner. So those cuts. And you fold the flaps up to get a box. So I'm going to make my attempt at drawing with perspective, and it might not go so great. So I have some base. It looks like I'm folding up, so this will become the height of the box. Let's see if we can establish what the volume of this box is. Let's see, it looks like this front side is going to be, you started with a side of length 2, you fold this up, so you reduce that side, a side of length 3. You fold that up, so you reduce its length by x. You reduce its length by x again, so what's the length of the front of the box? Yeah.
3 minus 2x.
Yeah, just 3 minus 2x. So apparently this length will be the exact same as that length, will be 3 minus 2x. What about the depth of the box? What will that be? Guess that should be the same as that length. And what will that length be? I start with the side of length 2, and then I'm going to fold up those two flaps. So I'll reduce that 2 by x and then by x again. So what length do I have left? 2 minus 2x. Nice. And now I have everything I need to write down the volume. The volume of a box is length times width times height. That seem reasonable? So let's suppose I asked you to, I don't know, find the choice of x that maximizes the volume of the box. You start with this piece of cardboard. You want to build a box that you can put as much stuff in as possible. We don't really have any algebraic techniques, but do you think we can look at a graph? Yeah, let's do that. And it looks like there are constraints on how big x can be. I'm making a cut of some length, so x won't be negative. So I don't care what happens when x is negative. What's the biggest x can be and still have this make sense? I think 1. If I cut a length bigger than 1, then my cuts would overlap on this side. So that gives me the domain to think about. So let's plot. Three minus 2x times 2 minus 2x times x from x equals 0 to x equals 1. Wolfram alpha is sometimes forgiving, but I don't think it'll make sense of that. That's what I wanted to plot, I hope. Let's scroll down and just take a look. Does it look like this function has a maximum value? And we can estimate it by just, I don't know, hovering over. What looks like it's the maximum value of this box? A little bit bigger than 1, and it happens at around an x value of 0.4. Okay, that's okay, but we could get a better estimate, right? We could zoom in. There's a range that I know should contain the maximum. So what does it look like where would you estimate the maximum volume of this box to be? 1.06. So yeah, but just by looking at this graph, which I know that was fast, but you guys have graphing tools that you could use on your own time. So by looking at a graph, it looks like the max volume is 1.06 achieved at x. Let's make it clear that this is approximate. What x value does it look like achieves that maximum volume? 0.29? Are there any units specified in the problem? I don't think there are, so okay, no units to put on. So, nice. That means if you want to even study just really basic geometry, you have no choice but to study polynomial functions. And maybe I'll even drop a quick sales pitch. Using techniques of calculus, you could find that x value that maximizes this explicitly on the nose. We're not going to do calculus, so I won't tell you that technique. So, the first thing to think about is graphs of polynomials. Graphs of degree 2 polynomials are really simple, right? They're either downward opening parabola or upward opening parabola. Let's see how much variety there is in polynomial functions. So let's go back. No. Here, I think maybe I even want to add like one more. No, I don't have space. Let's graph these. Those of you who have handheld graphing machines, go ahead and graph along. That includes like a phone graphing machine, though. Generally, entering in anything complicated on a phone screen is going to be tedious and annoying. So if you don't want to, I'll understand. But let's check out the graphs of these. Oh, maybe first x cubed. Is that actually one that we need a computer to graph, or do you guys just know what that graph looks like? You know what it looks like, right? It looks like it's got a wiggly point at 0. It curves up from there and down that way. So let's just answer some questions. How many zeros does that function have? Just one. Where maybe here are roots, zeros, x-intercepts. Those are all code words for the same thing. It's got one of those. How many turning points are there? How many points does this function change from increasing to decreasing or decreasing to increasing? Does it have any? It's got none. So it's possible for a degree 3 polynomial to think it's a degree 1 polynomial, according to those data. Let's keep on going. Let's plot x times 2x squared plus 1. And at the end of this document, we'll see some things about graphing by hand. Oh, damn it. X. So there it is. There's the graph. Oh, let's just go ahead and check. What's the degree of x times 2x squared plus 1? And we see what the graph looks like. It looks kind of like the graph of x cubed, but it doesn't quite get flat at x equals 0. Looks like it still has some slope. So there's a qualitative graph. Same questions. How many x-intercepts? How many turning points? Let's keep on going. There's one. X times 3x minus x times x minus 1, x plus 1. Yeah, that's the right number of parentheses. And I'll copy it down in a moment. How many turning points does that have? 2. How many intercepts?
Isn't it 3x?
Okay. Yeah. Thank you for saving me. Of course, I know what that'll do to the graph, right? It'll stretch it by a factor of 3, which in the things I actually have on the piece of paper, there is no scale. So I'll draw the same picture regardless. In fact, that looks like the same picture, right? The computer just has built that into the Y scale. And the answer to how many intercepts and turning points didn't change. So there's a copied down qualitative cartoon of that graph. I see 3 intercepts and 2 turning points. And let's do this last one. x times, ooh, what did I do? No, you couldn't see that anyway. Oh, damn it, that's not what I want. So same question. How many intercepts? How many turning points? Also 2? And all of those were degree 3. So before jumping down to this, all that'll change in this next one is I'll change the viewing window to explicitly be really, really big. I want to forget what happens for small numbers, and I only want to see what happens for big numbers is what I'll do. But let's think about these two. So in general, a degree d polynomial is going to have at most whatever the degree of the polynomial is, number of turning points. Every degree 3 polynomial will have at most 3, nope, not turning points, intercepts. What I wrote, not what I said. A degree 3 polynomial has at most 3 intercepts, and that agrees with the graphs, right? The biggest number we saw for those degree 3 polynomials was 3 intercepts. The greatest number of turning points we can have is 2. And we don't have to have exactly 2. Oh, damn it. It was 2 then, because 3 minus 1 is 2. If you have a degree 4 polynomial, it might have up to 3 turning points. Have a degree 5 polynomial, it might have up to 4 turning points. And we see that it doesn't need to be exactly that. It's at most. And that at most is going to complicate things. If I give you any degree 2 polynomial, how many turning points will it absolutely definitely have? 1. It won't ever have 0. But we see a degree 3 polynomial sometimes can have only 0 turning points. So next, let's think about what happens when we zoom out really, really far. And I think I'm even going to plot all 3 of these at the same time. X cubed, x times 2x squared plus 1, 3x, x minus 1, x plus 1, x times x minus 1 squared. Did I copy all those down correctly? Okay. From x equal to negative 1,000 to x equal 1,000. No, it's not going to be happy. All right, let's do them one at a time. That's annoying. So, x cubed from negative 1,000 to 1,000. I see something that that looks qualitatively like x cubed on a small viewing window too. So, up to rescaling, x cubed looks like x cubed. Let's grab the next one. Let's see if I can get at least cubed and that. Oh, okay. There. Okay, so there's the graph of x cubed along with x times 2x squared plus 1. So let's even decide to distribute, which, sure. That is the same as x times 2x squared plus 1. How does it look like at this scale? Do those two look like the exact same graph? Not quite, but they look really similar. How would you want to go from the blue one to the red one? Looks kind of like it's just stretched a bit. All the y values have gotten more extreme. So, in this picture, qualitatively, I can't tell the difference, but maybe I'll say that this looks like it's pretty close to just being 2x cubed. 3x times x plus 1 times x minus 1. So maybe before we even look at the graph, what do you, oh yeah. Before I even scroll down and show you the graph, how do you think these two will compare? Okay, cool. Let's just see how they compare. So there's 3 times x minus 1 times x plus 1. Yeah, that's the same as what I typed. And there's just x cubed. How would you want to go from that blue graph to that red graph? Again, it's just a vertical stretch. Maybe you can't tell that it's exactly by this in this picture, but it turns out it's stretching by a factor of 3. And what do you think should happen if it's x times x minus 1 squared? How should that compare with the graph of just x cubed? Right, here are a few assessments. Let's see a picture. X times x minus 1 squared. From negative 1,000 to 1,000. So any small changes in the graphs we just won't see. So what we're going to see here is how these graphs look just at a very macro scale. I'm going to forget all the small details. How do the two graphs look like they compare? I can't tell the difference at this scale. In general, whenever you want macro pictures, big scale pictures of what any polynomial looks like, you don't need to do any more. If I give you a degree d polynomial, so there's the top degree and lower degree stuff. If I zoom out far enough, if I forget enough detail, it will look like the graph of the top degree term, and that's it. So maybe it's worth saying this in an application. So if I want to give you the graph of negative 7x to the 4th plus 3x cubed plus 2x squared plus 5x minus 23, and I viewed that over a really, really big window, what would that look like? Yeah, but it's just in there.
Whatever x to the 4th looks like.
Yeah, well, with a negative 7 in front of it. So this will be approximately the same as negative 7x to the 4th. And maybe we can even see that. Let's graph negative 7x to the 4th plus 3x cubed plus 2x squared minus 5x minus 23. I think I screwed up some of the terms, but that doesn't actually matter. Right? The example will still be relevant. As compared to negative 7x to the 4th. Oh yeah, I'm sorry. So there's the two polynomials. I've screwed up some of the coefficients in the one of them, but that doesn't matter because I made them up on the spot anyhow. How do those two graphs compare? I can't tell the difference. So that's all this is saying. If you want the big scale picture of what the graph of a polynomial looks like, just look at the leading term. And somehow that makes sense. When x is like 25 billion, well, okay, when x is like 1,000, x to the 4th will be like a 4 times 3 digit number. X cubed will be a 3 times 3 digit number. This is way bigger than that. The other terms are so small they don't make a difference. So let's keep on going just a little bit. Let's put these together and just answer some questions about this polynomial. If you were to encounter this polynomial, let's try to decide how big the degree of that polynomial should be. How many roots does it have? It's got one root. So that says the degree should be at least 1. But could this possibly be a degree 1 polynomial? Why not? It's got 2 turning points. So what does that say the degree has to be at least? Degree at least 3. Oh, sorry. D minus 1 turning points. So D minus 1 is bigger than or equal to 2. D is bigger than or equal to 3. So that says that it is a polynomial degree at least 3. Next, let's think about the macro scale, the big picture scale of it. If you want to imagine the arrows going on forever, and I just covered up what happens in the middle, so that's like forgetting all the small details. Does that look like it could be a degree 3? Does that look like it could be x cubed in the middle? Yeah. So the macro scale still thinks it could be degree 3. Could this polynomial conceivably be a degree 5 polynomial? It could conceivably, but I wanted the smallest degree. So let's look back. So the next thing that I want to think about is if you have a polynomial that's totally factored, how can you read off the graph without using a machine? Right? Knowing what the graph should look like in advance is really useful in that it lets you cut out the machine and just make intuitive statements easier. So let's try to recover the graph of x times x minus 1 squared. So maybe I'll just recover the graph right now. So there's the graph of that polynomial. It's got 2 roots, right? It's got a root at x equal to 0, right here, and another one at x equal to 1, right here. But locally, if you just look really, really close to those 2 roots, you see different looking pictures. And in order to, I could do one thing. I could like zoom in really, really close on them in this picture. So there's one of the roots locally. There's a local picture of the other root. If you only saw that much of a graph, what would you say that that function looks like it is? What degree polynomial would you say that is? You would say it looks like a degree 1 polynomial. If you only saw this much, what would you say it looks like locally? 2. That's the difference. So at x equal to 0, it looks linear. At x equal to 1, it looks quadratic. More precisely, if we were to zoom in really, really close at x equals 1, we would just see a line. Oh, I didn't zoom out far enough. Sorry. And that's all we did see. We could go to the computer and also see it, but I think I just want to save that time. So maybe I'll say here's something that you guys should do on your own time. Take exactly this polynomial. Take a viewing window really, really close to 0. Like, I don't know, 0.001 to negative 0.001. Look at the graph. It should look linear. Similarly, if we just look really, really close to 1, so from 0.999 to 1.001, I claim we'll just see a parabola. And I assert that we could have actually known that beforehand just by looking at the polynomial, because of the following fact. If I give you a polynomial and it happens to factor, so if p of x factors is some other polynomial q of x times the power of c minus p, x minus c, with q of c is equal to 0, then close to x equals c, the graph of p of x will look like q of c times x minus c to the p. So that looks abstract, but let me just put in words what this says. To graph p of x close to x equals c, here's all you need to do. find the factors that give this root at C, because that's what the x minus c to the p was. If you plug in x equals c, this term becomes 0. That term, by assumption, does not become 0. And remember these. And then just plug x equals c into all remaining factors. Does that make sense? That's the same as this says in WAT. I've plugged c in for x to all the factors that don't give me 0. And I've remembered all the pieces that do give me 0. That makes sense? So let's just see this in practice on the next page. I should have enough time to make it through one of these two examples. So let's sketch, without consulting a machine, a qualitative cartoon of a graph. Let's sketch qualitatively the graph of x times x plus 1 squared times x minus 2 cubed. And let's do it by checking these things. So let's find the roots of this first. Is it easy to see where this polynomial is equal to 0? Yeah, you would set it equal to 0. That would be x times x plus 1 squared x minus 2 cubed equals 0. The only way a product can be 0 is if one of the things is 0. Oh, yeah. So the only way this polynomial, which is the same as that, can be 0 is if x is equal to 0, or x plus 1 is equal to 0, or x minus 2 equals 0. So what are all of the zeros of this polynomial? 0, -1, and 2. So I'll just put those as dots for now. There's x equals 0. There's x equals -1. There's x equals 2. I won't worry too much about having a scale that's reasonable, because my techniques won't allow for a reasonable scale anyway. But those are about where you would want -1, 0, and 2 to be, I think. So now let's figure out what the graph should look like close to each of these points. So near x equals 0, I should remember the factor that results in a 0 at 0. So I should remember the x term. Then I'll just plug in x equals 0 for all the remaining pieces. So I'll get x times plug in 0 for x. 0 plus 1 squared times 0 minus 2 cubed. That's 0 times, no, god damn it. That's x times 1 squared is 1. What's -2 cubed? I think it's -8. So close to x equals 0, I should see something that looks like the graph of -8x. What does the graph of -8x look like? Straight line, slope -8. And I won't worry about scale, but I should be able to tell that it has negatives. So it should look like a straight line with negative slope close to 0. Close to x equals -1, I'll play the exact same game. I should get, well, I'll remember the term that gives me a 0 at -1. It was x plus 1's fault that this polynomial is 0 when x equals -1. So I'll remember the x plus 1 squared term. And then I'll plug in -1 for everything else. So that'll be -1 times x plus 1 squared times -3 cubed. And let's even just be vague so we can be easy about things. X plus 1 squared. It'll be x plus 1 squared times something positive or something negative. Positive, I think, because I'll see one negative sign and 3 more negative signs. So maybe you know that it'll even total up to positive 27, but I don't. So it'll be a positive number times x plus 1 squared. So it should be a parabola with vortex at 1, 0, upward opening or downward. And, well, maybe I'll oh no, it'll be positive. Close to the intercept at 2, I'll wind up with a positive number times x minus 2 cubed. So, close to x minus 2, I should see a degree 3 polynomial, something that looks like x cubed. So the whole graph should wind up looking something like that. I'll just interpolate between smoothly. What's the degree of this whole polynomial? 6, I think. If you imagine FOILing it out, you would wind up with an x to the 6th term. So, big picture, it should look like x to the 6th. X to the 6th looks about like that asymptotically. So there's a cartoon picture of the graph. And while you guys pack up, I'll just do one thing to check if this is a non-nonsensical picture. I can graph it electronically also. Let's do that just to check if these things look reasonable. X times how did we do? Is their graph qualitatively similar to that graph? And that's good enough for me. I couldn't tell how big that peak and that valley were, but I could tell there was a peak and a valley. Okay.
Or they tracked me. I should have told you sooner, but I didn't know I was racing until late yesterday. We had class yesterday, so if you need like a slip or anything, I can get you the paper that has the signature of my coach.
Yeah, you should, just to really make it be excused. On the other hand, the thing on the schedule for Friday is more lecture.
Okay.
So you'll be missing lecture. I won't be collecting anything on Friday.
Okay.
So it doesn't really matter if it's excused or not.
Okay.
But yeah, you should be in the practice of sending me a copy of the thing.
I was just wondering if you brought the homework that we turned in last week back. Because I think I might have accidentally slipped in the Monday work that's due today from last week into it.
I'm not done processing it, so I'll give it back to you tomorrow. In the meantime, I mean, we'll just have to wind up redoing those problems. It'll be easy for you too because you've already done them.
Okay.
And if it's not easy to do, then you need to do it anyway because that's what you're going to do. Oh, okay. You missed an announcement. That's it. Why don't people ask me questions about this almost I'm going to collect it tomorrow. Are you going to be here tomorrow? Yeah. Okay, cool.
Just wanted to make sure that it's just these four from last week. Assignments due. Just to make sure.
Yeah, it should be the four of those. It should be which days? It should be the four assignments between Monday and Friday.
Making sure I have the things that worksheets.
I think one of them did have, today is the 26th. This is today. So this one doesn't have any worksheets. That one doesn't. That one doesn't. Monday does. Monday has these problems.
Oh, I got you.
Yeah. Did you do those problems?
Yeah.
Okay, yeah.
All right.
Thank you.